Okay, so in this video, I want to talk about horizontal asymptotes of rational functions. So I'm looking at a function that is one polynomial over another polynomial, and I'm considering what's happening as x is going to infinity. What is the end behavior of this function? And this is going to build off the last video, the growth rate of functions. So basically, there are three scenarios here, and each of them something different happens. So the first scenario is that if the degree of p is equal to the degree of q. So for example, if we have a quadratic over a quadratic or a cubic over a cubic. Let's actually do an example here. So let's do an example. If f of x is 5x cubed plus 17x squared minus 2 divided by 2x cubed plus x plus 10. It's a cubic divided by a cubic, so the degrees are both 3. Now, from the previous video, the growth rate video, we know that this 5x cubed is much, as x is going to infinity, what's happening? This 5x cubed is much bigger than 17x squared and much bigger than -2. So as x goes to infinity, 5x cubed plus 17x squared minus 2 is dominated by 5x cubed. It's looking like 5x cubed. There's this thing that's really big and everything else is small compared to it. And we'll make this notation precise later, what I mean. But basically how you should think of it is it's growing like 5x cubed. And similarly, 2x cubed plus x plus 10 is growing like 2x cubed. And so if I consider this function, f of x, as x goes to infinity, this function, so I'm writing is approximately, and what I mean is as x is getting really large, this function is approximately behaving like 5x cubed divided by 2x cubed. And now this function we understand actually exactly. If x is 0, this function's undefined, but we're thinking about what's happening when x is large anyway. For every other x, this function is just equal to 5/2. So what I'm saying is this function f of x is behaving like, as x goes to infinity, 5/2. And you can think about what's happening in any scenario where the degree of p is equal to the degree of q. Well, basically the function is going to behave like the leading term divided by the leading term. And now since the degrees are equal, we can sort of think of canceling out this x cubed or canceling out the x's in the leading term. And so basically what's happening is the end behavior is going to look like the ratio of the coefficient, the leading coefficients here. Okay? Now there are two other scenarios. What happens when the degree of p is less than the degree of q? So now, let's do an example. F of x, let's use the same numerator, 5x cubed plus 17x squared minus 2, and let's divide just by x to the 4th now. So now the degree of the denominator is bigger. And this reasoning is going to be true for any degree polynomial that's bigger than 3. So this could be degree 5 or 6 or 7 or whatever. And now using kind of the same logic, this is going to behave as x goes to infinity. This is going to behave like 5x cubed divided by x to the 4th. And now this is the same function as long as x is not equal to 0. This is the same function as 5 over x. And so now I'm taking 5. If I want to understand how does this function behave as x goes to infinity, I'm taking 5, a finite number, and I'm dividing by x, which is getting really large. So x is bigger than any number you can think of. And so this fraction is getting very, very close to 0, right? As the larger x gets, the closer this fraction is looking to 0. And so this is tending towards 0. Let's write it that way. And we'll make that precise later. We'll make this notation precise in the next section. So if the degree of p is less than the degree of q, this is sort of always going to happen. It's going to behave like the leading term in the numerator divided by something of a bigger power. And as we saw in the growth rate video, if the polynomial has a larger power, it's going to be much bigger. And so you're taking a numerator, you're dividing it by something much bigger, and so it's going to 0. Okay, now, the final situation here is if the degree of p is bigger than the degree of q. So this is the degree of p is bigger than the degree of q. And now let's use the same numerator here, 5x cubed plus 17x squared minus 2. And let's use the denominator is 100 times x. Now, using the same logic here, this is going to behave as x goes to infinity. This is going to behave almost like 5x cubed over 100x. And now this is the same function as long as x is not 0 as 5x squared divided by 100. And so now in this situation, I'm dividing something that's getting extremely large, 5x squared, by something finite, right? So I'm dividing by something. You should think of this as dividing by a really small number, right? So if I'm taking something going to infinity, I'm dividing it by something finite, this is also going to get extremely large. So basically, this is the only situation where there's not going to be an asymptote, right? There's not going to be a horizontal asymptote. If the degree of p is bigger than the degree of q, then your function is going to either tend to positive or negative infinity. It's going to either get very large, or if this was a negative 5x cubed, it would get very negative, right? The first two situations, there is a horizontal asymptote. So if the degree of p is equal to the degree of q, this function is looking like a finite number. And so as x is getting really large, if I could zoom out and see the whole x-axis, the function is tending towards the line y equals 5 halves. It's getting very close to the line y equals 5 halves. And in the situation where the degree of p is less than the degree of q, the same thing's happening. It's just that the line that it's tending towards is the line y equals 0. So in both of these first two cases, the function is getting very close to a horizontal line. So it's tending towards a horizontal asymptote. In the third case, we don't have a horizontal asymptote.